Welcome to The Quantum State, a podcast exploring the latest research and innovation in quantum computing. Join us as we dive into groundbreaking breakthroughs, trends, and news shaping the quantum landscape. Hello, everyone, and welcome back to The Quantum State. Today, we're joined by Yuval Boger, the CMO of QuEra. So, Yuval, can you introduce yourself and correct my pronunciation and share how you actually got into the quantum computing space?
It's great to be here. So my name is Yuval Boger. I'm Chief Marketing Officer of QuEra. Some people say QuEra. Either way is fine as long as you spell it right. I got into the quantum space actually with a previous company, with Classic. They make a software platform for synthesizing circuits from high-level models. And I was Chief Marketing Officer there. And then after a while in the software side, I decided to cross over to hardware. And that's where I am at QuEra.
Hi, Yuval. Can you tell us about QuEra's technology, in particular the physical platform that you're working on, which is large-scale arrays of atoms? How does that process work? How do the qubits, how are they defined in that system? And what makes this unique or in some way better than other competing platforms?
As you said, we make quantum computers based on neutral atoms. And although I get paid to say that, I do believe that neutral atoms is the best way to build quantum computers. And I think that we can prove that QuEra is the most advanced vendor in neutral atoms. So the qubits in neutral atoms are individual atoms. We use rubidium atoms, others use other types. These atoms are suspended in air or in vacuum by tiny laser beams, optical tweezers. They hold them in place. And then they can also, because they're trapped in the optical tweezer, they can be moved around. When atoms are nearby, with the right set of laser pulses, they can entangle or otherwise interact. When they're far away, they do not. So processing in neutral atoms is about bringing the right atoms together, executing the correct sequence of pulses, and then, of course, ultimately measuring them. And that can happen in two ways. Our first computer, which is live on Amazon Bracket since November 22, works in what's called analog mode. And in analog mode, you take a particular problem, you arrange the qubits geometrically, and through the geometry, you can encode a lot of the constraints or a lot of the things that you care about in the problem. Could be an optimization problem, could be a simulation, and so on. And then the user defines essentially a time-dependent Hamiltonian that says this is how the system evolves over time. You execute that, and then you take a photograph essentially and measure the qubits. This is analog processing. We're working on next-generation systems that are more traditional gate-based, where we use the same type of technology to implement quantum gates. The reason neutral atom platforms are unique, well, there are a couple of reasons. First, the qubits are, we sometimes say, nature's perfect qubits. They're precisely identical. You can make 1 million of them with no manufacturing defects. The lasers that hold these qubits in place, because they're held in place, they're essentially cooling them to microkelvin temperatures, very, very close to absolute zero. So neutral atom computers do not require cryogenic cooling like other systems do, which makes them much easier and quieter, but much easier to deploy. Because these qubits can move, we achieve all-to-all connectivity. So if you're a superconducting qubit, you can only talk, you can only interact with neighboring qubits, 2, 3, 6, depending on the architecture. And therefore, if you have two qubits that are far away, they have to go through a lot of swap operations to be able to interact. With neutral atoms, that's not the case. You can just move the qubits next to each other and cause them to interact. And this ability to move qubits, to shuttle qubits while maintaining their quantum state, allows you to create algorithms that are more efficient, allows you, perhaps we'll talk about later, to create error correction codes that are more efficient. And so it has a lot of advantages. And last, several labs have shown neutral atom arrays of even 10,000 qubits or 10,000 atoms. So while other technologies start to require optical interconnects after a few hundred qubits, we are very far from that. We can go to tens of thousands of qubits without needing to create interconnects between multiple systems.
Just a follow-up on that. So the way you've described it, you need to physically move around the qubits to get them to interact in a nearest neighbor fashion. That, as you said, gives a lot of versatility because you can get complete connectivity in the architecture. But the actual physical movement, I mean, that's going to impose a bottleneck on the speed. How quickly can you actually move the qubits, and to what extent is the need to geometrically relocate qubits a limiting factor in this architecture?
So the qubits actually move very fast. Qubits can move from one location to the other within a few microseconds. And part of the reason, of course, is that they don't need to move very long distances. In a normal operation, qubits might find themselves 2, 3, 4 microns away from each other. So a qubit that's far away may be 50 microns, so it doesn't take that long to move it. If you think about, but I think you brought up a good point. Speed is often considered one disadvantage of neutral atom arrays. So let me address that. When we work in analog mode today, the system that's been up since November of 22 on Amazon Bracket, now it's up 130 hours a week, we allow running about 4 shots a second. So you can, but what do these shots include? So you basically say, okay, I have a specific problem. I'm moving all the atoms to where I want them to be. I then execute the time-dependent Hamiltonian. That could be just a few microseconds. And then I take a picture. What's taking time is both moving the atoms originally into place, as well as the taking picture part. And in today's system, if you're familiar with the game Connect 4, where you try to arrange 4 in a row, once the game ends, you sort of pull the bar at the bottom of the board and all the pieces fall and you have to start afresh. This is what happens in our existing computer. After you measure, you basically have to reload everything. But now you can start thinking about improvements. First, you have a lot of qubits, so you can actually execute a lot of algorithms even in parallel. So if you're trying to run something that doesn't require the full set of qubits, you can basically run multiple copies of it. The other thing is we could envision working with camera manufacturers or even non-camera sensors to provide faster readout. Instead of taking a photo of everything, just take a photo of what you need or some other ideas. And then who says you need to reset the board every time? So if there was a way to leave most of these pieces in place, then you could do a lot of other things. So while neutral atom quantum computers are, on one hand, super powerful, on the other hand, they're a little bit slow, there are many orders of magnitude where we can improve the speed.
So, there was a great announcement in December of last year about QuEra achieving a large number of logical qubits. I think 48 was the number. Can you explain what this means for quantum computing? And also, can you comment on when you expect to see a break-even point where the error correction is actually improving things?
Sure. So I think you're referring to a December 23 paper in Nature that was published. That was an experiment that was done by Harvard with participation from QuEra, University of Maryland, MIT, and NIST, and was performed also at Harvard. And in this experiment, the team indeed performed complex algorithms with logical qubits. So let's sort of go step by step. Qubits today, as wonderful as they are fragile. They are very susceptible to environmental noise to imperfect controls to laser noise, whatever the technology is, there are errors that are inherent in qubits. And so when you look at sort of the state of the art of, say, 2-qubit gate fidelity, meaning if you have a 2-qubit operation like a CNOT, how many times is it going to be successful and how many times is it going to fail? The state of the art is roughly 99.9%, which sounds like a lot, but it means that 1 in 1,000, you're going to get error. And compare that with classical computers where the error rate is essentially negligible. It's maybe 10 to the minus 13 or 14 or 15. And so how do you close that gap? The reason you need to close that gap is if you want to run sophisticated, complex algorithms, you need a lot of operations. So for instance, the UK National Quantum Program, and we just won a contract to deliver a computer to that program, set a goal of having 1 million QOPs, 1 million quantum operations by 2028. So people need to bridge that gap between the 10 to the minus 3 or 10 to the minus 4 error rate to something much, much better. And it's unlikely that that's going to all come from just making better qubits. So the solution is to make what's called logical qubits. And logical qubits are the quantum equivalent of the classical repetition code. So if we were talking on a very noisy line and I wanted to give you my credit card number, and let's say my credit card number starts with 6 and then 7, maybe I would say 666 and 777. So I would repeat every digit 3 times or 5 times or 19 times, so that if there was an error, if there was noise on the line, you could detect that one of these is incorrect and then find the right digit. Unfortunately, physics prevents us from just duplicating qubits. That's a good thing if you're doing quantum communications. It's not a great thing if you're doing quantum computing. So logical qubits are a collection of physical qubits that spread around the information in such a way that you could detect an error, and in some cases, depending on the particular error correction code, you could correct error. Until the Harvard experiment, the state of the art was 1, 2, or 3 logical qubits. I think I may be confused in who's doing what, but I think there was an IBM paper, there was a Google paper, maybe a Quantinuum paper, but they were all in the 1, 2, or 3 logical qubits. For the first time, we were able to execute an algorithm with 48 logical qubits. So much, much more, and starting to get interesting. In fact, if you had perfect logical qubits that were just completely error corrected, you're essentially approaching the simulation limit. You're approaching the number of qubits that could be simulated on sort of today's fastest supercomputer. So that was a fantastically important experiment. I think Scott Aronson called it the most important experimental result of 2023. And it showed a couple of things. First, it showed that as we increase what's called the code distance. So when you do an error correction code, there's something called the code distance. A code distance of 3 means that you can correct 1 error. Code distance of 5 means that you can correct 2 errors. Code distance of 7, 3 errors, and so on and so on. And the team showed that when you increase the code distance, indeed, you're getting better and better qubits. You're using more physical qubits, but you're getting better qubits. And then it was able to execute some really complex algorithms. So that's the significance. And that paper also had some other breakthroughs that I think are very, very important to understand sort of the scalability questions of quantum computers, because computers with 30 qubits, even if they're perfect qubits, are not truly interesting. You want to get to thousands or tens of thousands or even more qubits. When you think about an architecture like a superconducting architecture, each superconducting qubit has 2 or 3 wires going into it. And so if you have 10,000 qubits, you're going to have 20,000 or 30,000 wires going into that computer. That's a lot of wires. It's very heavy. That's very expensive. That's very noisy. How do you cool them? How do you route them? So it's almost like imagining if you opened your television set and found a wire going into every pixel. That would be a really large and heavy television set. Instead, what that paper showed is what we call the zoned architecture. And the zoned architecture is a little bit like the von Neumann architecture of classical machines. So if you think about your CPU, classical CPU, it has registers and it has memory. And what the CPU does, it pulls data from memory, brings it into registers, does something on it, and then sends it back. And by the way, you can double the memory without replacing the CPU. So the team showed an architecture that had three zones. One is essentially a storage area where qubits can live for a very long time. The other is an entanglement area where you could sort of pull qubits or patches of qubits, logical qubits, from the storage area into the entanglement area and operate them and then put them back. And then a measurement area where you could use for either mid-circuit measurement or end of computation measurement. The team showed that they were able to do an experiment that had about 300 qubits with only 10 or so control lines. Compare that with 300 superconducting qubits where you'd need almost 1,000 control lines. So in this architecture, the number of controls scales, let's call it logarithmically, with the number of qubits and not linearly. So that's one more reason that we're very, very hopeful that neutral atom computers can scale to a useful scale.
Great. And when do you expect to see a break-even point where you're actually really going to be able to store quantum information longer in the codes?
So the paper showed that longer codes are better, so you get better fidelity. So that's great. It does require, which we've shown, if the physical qubits are totally lousy, then no logical qubits are going to help them. So it's sort of generally accepted that you need about a 99% 2-qubit gate fidelity for physical qubits to be able to do error correction. The Harvard team with QuEra and others has demonstrated 99.5% fidelity, so better than what's required. And one of the amazing things about QuEra is that QuEra has been able to productize innovations both from QuEra labs as well as from our MIT and Harvard collaborators and move them into the market. That's one reason that when we launched our first neutral atom 256 qubit quantum computer in November of 22, we were the first neutral atom computer to be publicly accessible. 15 or 16 months later, we remain the only neutral atom computer that's publicly accessible. And part of that is because we're able to productize those innovations very, very quickly. So last month, we had announced our 3-year roadmap. And we basically said in 2024, we're going to have a computer that has at least 256 physical qubits and at least 10 logical qubits. Which is interesting. A year later, in 25, we expect to have about 3,000 physical qubits and about 30 logical qubits. And a year later, in 26, we expect to have north of 10,000 physical qubits and about 100 logical qubits. And when we go sometimes between 30 and 100, you get to sort of that twilight zone where you say, well, I can't simulate it classically anymore. Now we're entering this area of new discovery. And we just can't wait to see what people are going to be able to do with it. So the short answer to your question is this year, we will allow early customers to start using our 10 logical qubit computer. And a year later, the 30 logical qubit computer and so on. And of course, once we get enough experience with what customers are doing, we will roll it into the market, either as delivered on premises to customers that want to purchase such a computer or put it on some version of a cloud.
Great.
Definitely. I'd like to hear more about that roadmap. So it's very ambitious to get there by 2026. So can you break down the roadmap a little bit more about each step along the way and what you're expecting to see as opportunities for each one and challenges that you think you're going to face for each step?
So the roadmap is ambitious, but I think I quoted Scott Aronson earlier. John Preskill wrote on X that QuEra's roadmap is ambitious but not crazy, which I think is sort of the perfect combination. If he said, "Oh, it's not ambitious enough," we would have been worried, and if he said it's crazy, we would have been worried as well. So we're happy to see that. The 2024 computer requires us to do things that we haven't. We've shown in the labs, we haven't made available to others, whether it's digital gates, whether it's the ability to shuttle qubits while maintaining their quantum state, the ability to measure qubits, the further improvement in the fidelity of both single qubit gates and 2-qubit gates, and so on. I think in 2025, we'll start seeing non-Clifford gates, so have a sort of a broader selection of gates. And in 2026, even more. A 10-qubit machine, a 10 logical qubit machine, is interesting for research and is interesting to start understanding error correction codes and how to work with logical qubits. Of course, a 10-qubit machine by itself is not super interesting. You could simulate that on your phone in much lower cost, and it's going to be much easier for you. But we do think that we are in this transition period where at some point, and maybe it's 2026, people will no longer care how many physical qubits we have, just like you may not care how many transistors are in your phone. Lots. The point is, I've got error-corrected qubits. I can do multiple rounds of error correction, so I can run lengthy algorithms, and I think that's where it gets really, really interesting.
We've spoken a bit about the need for error correction, and this is a whole nuanced field on its own, and there are many different types of codes that you've alluded to. They all have different sort of distinct implications for different physical implementations. In the architecture that you're working with and the codes that you're working with, what are the limitations and what are the challenges? So, for example, once you're dealing with error-corrected logical qubits, you have to do all of your gates on those encoded qubits now. It's not just taking the physical type of gates and applying them directly. It has to be converted into the code space. So in those terms, are you able to do all of the necessary gates on encoded qubits? Are there any fundamental architectural limitations that might be an obstacle? And perhaps one further qualification is there's also a distinction between error correction and fault tolerance. And lots of people talk about error correction having been achieved to different levels, but fault tolerance is the ultimate goal, whereby the error correction is used in ongoing rounds to maintain a computation with coherence over the course of the execution. How far off is that more ambitious target of fault tolerance versus simple logical error correction?
So the goal is certainly to be able to perform multiple rounds of error correction, meaning to perform operations, to detect and correct errors, and to continue that in the calculation. So that's certainly part of the roadmap. One advantage of the atom moving architecture, or the ability to move qubits around, is that you can implement more efficient error correction codes, meaning that you would require fewer physical qubits for a logical qubit. And there were two papers, one from IBM Research and one from Harvard and QuEra and others, that spoke about QLDPC code, quantum low density codes. And they basically showed that with higher connectivity, you can get more efficient code, as opposed to having to do what's, I think, sometimes called lattice surgery if the qubits are static. One interesting thing in the architecture that was published in that Harvard paper is the ability to do transversal gates or parallel gates. And what I mean by that is, imagine that my hand was a logical qubit. It's not a very good one. It only has 5 physical qubits. And let's imagine that this other hand is also a logical qubit. Well, we can move them and basically interleave the qubits, interleave the physical qubits, and then with a single or set of laser pulses, simultaneously entangle or simultaneously operate on every pair of physical qubits, thereby performing that operation on the logical qubits. And then, of course, we can take these qubits back and take another patch of qubits, another logical qubit, and do the same. So the nice thing with the architectures is essentially anything you can do on a physical qubit, you can do on a logical qubit.
Yeah, so just a question on the architecture. I'm curious, what stops you from going to 3 dimensions? So like with optical lattice trapping of neutral atoms, you can naturally go to 3 dimensions. And I know this is using a different optical trapping technique with tweezer type trapping. But is there any fundamental reason, or is that something that you're thinking of as a company?
I think it's more of an engineering choice. We don't think that we need to go to 3 dimensions. Obviously, when you go to 3 dimension, it introduces, or if we went to 2 types of atoms or any other variations in the neutral atom space, it introduces some opportunities, but it introduces a new set of complexity and challenges to overcome. And so we feel very, very comfortable with our 2D choice at the moment.
And in terms of connecting modules, what does QuEra have in mind there? I know there are various proposals for architectures like trapped ions and superconducting devices, where you would use, as you mentioned earlier, basic electromagnetic couplings, either at the microwave or optical frequencies. And Photonic is also considering this. What does QuEra have in mind for connecting modules?
So we're definitely thinking about this and exploring different avenues. But for us, the need to do that is much farther away than with others, because we have seen, and it's again, not just QuEra, you can see it in many places, arrays of 10,000 qubits or tens of thousands of qubits that could reside on a single location. And therefore, only when we get to, say, 100,000, give or take, or maybe 50,000, then we would need these type of interconnects. So right now, if you look at our next 3 years, when we're promising a 10,000 qubit system, we still don't need to go to these interconnects. But of course, we're thinking ahead on how would we best implement it once the need arrives.
Great. And then just the last question on hardware. You mentioned the accessibility through Amazon Bracket. And could you just explain some of the opportunities this could offer to users around the world? Like what kinds of fun simulations do you have in mind that people could try out? Or have you been contacted by researchers who would like to get their hands on these devices?
So the wonderful thing about being on Amazon Bracket is that it's universally accessible for a very, very low cost. So if you have a AWS account, you can start using it. There's a price calculator on the Bracket website, but it's very inexpensive. It's really pay as you go. If you run a little bit experiment, you pay a little bit of money. I mean, there are also starter packs that give you some usage for free. And because of that, we are seeing users from all over the world. We're seeing papers that are published both by academic research. We have seen papers from BMW, and we've seen work by JP Morgan and others. So anyone that's listening can just sort of whip out their credit card, or maybe they already have an account, and use it online. So that is one advantage. The other advantage is that you can run hybrid algorithm. Amazon or AWS, of course, has a wonderful classical compute infrastructure. So if you want to run something that runs partially classical and partially quantum, that's easy to configure. The downside of what used to be the downside of public cloud access is that it's public. So if you want to have a barbecue in the park and someone else is already having that barbecue, you need to move to a different location. So sometimes you would have to just wait in the queue behind others. Recently, together with Amazon, we introduced sort of reserved time slots where you can choose to pay a little bit more, but say, you know, the machine is mine from this time to this time, so you know what you're running. But I think ultimately, we're seeing more and more companies and also national programs that want to have their own on-site, on-premise quantum computer. And they might want to do that for a number of reasons. One reason is control. Who's running and who has priority. The other reason might be tight integration into classical data center. A third reason could be data residency. Okay, I've got sensitive data. Do I want it to leave the company? Do I want it to leave the country? Where is it going on the cloud? Whereas if I have a computer on premises, I know exactly where it is. And a lot of countries are using these purchases to jumpstart the local quantum ecosystem, understanding that quantum is such a strategic technology that they need to create startups and education programs and workforce development and others, and also encourage large existing corporations to work in quantum. And purchasing the computer is one way to do that.
Yeah, so you mentioned a little bit about this twilight zone that you have between the 30 logical qubits and the 100 logical qubits between 2025 and 2026. And then you mentioned BMW, JP Morgan are already using your systems and starting to explore. So with that kind of transition to the larger sets of logical qubits, what kind of advantage are companies like BMW and JP Morgan going to see in their space? So, for example, we've talked a lot here about pharma, material science, financial applications. What are they really trying to do with quantum computers?
So I think today they're trying to optimize their algorithms and to learn. But if you can run a molecular simulation on 10 qubits or 20 qubits, then you can run a simulation of a larger molecule with 50 qubits and an even larger molecule on 100. And at some point, it becomes interesting because you can run something that you can do more accurately or faster or just with lower energy than on classical computers. The same would go for optimization problems. If you're trying to optimize, sort of a traveling salesperson problem, or which technician goes where and when, then there's a gap or there's a transition between toy problems. Oh yeah, I could solve this classically, but I just want to make sure that the algorithm works, to, oh, I couldn't solve this classically, or I couldn't solve this classically fast enough based on changing conditions. So I think a lot of companies are getting ready for that time. And one of the things that the Harvard paper that you mentioned from December of last year did is we saw a lot of customers that came to us and said, well, we thought that that point of true usefulness for quantum is going to be 5 years away. But based on the results that Harvard and QuEra and others have shown, that shrunk the timeline for us. And maybe now it's 3 years away or 2 years away. So we better get going so we don't have one of our competitors that's taking advantage of these capabilities while we still don't have the expertise to use them.
Are you seeing right now within the customer base that these teams using your systems are more dedicated quantum scientists, or are they domain experts within different fields trying to learn about quantum?
We are seeing 3 types of applications. We're seeing simulation that's typically more from the scientific community, exotic phases of matter, spin liquids, all kind of things that were perhaps predicted but now can be measured. We're seeing optimization problems that are more of an industrial nature. And then we're seeing machine learning. And so, for instance, a couple months ago, we had a webinar together with Deloitte Consulting, and they used our machine learning workflow, an algorithm called quantum reservoir computing. And they showed multiple results for medical, for inspection, for predicting home prices, where the quantum workflow generated better results than a generic classical algorithm. So they're not claiming quantum advantage in the, oh, we beat the best classical algorithm, but if you take a generic workflow, then the quantum one actually did much better. And that webinar is available online. You can certainly see the results and what reservoir computing is about. And so that's another application. So simulation, optimization, and machine learning are things that we're seeing people experiment with today.
What do you see as the most important priorities for the not just yourself, but for the field as a whole, in terms of getting quantum computing to the next major stage in its evolution? What do you see as the number one thing that needs to be addressed in the field as a whole?
So in general, everyone is talking about, well, I'm going to do all these wonderful things once the computers are larger. So every technology has their own barrier to what larger means and what's stopping them from being larger. So for instance, one of the things that one has to overcome with neutral atoms is laser power. If we need a certain amount of laser power to hold an atom in place, if we have many more atoms, we need either more lasers or stronger lasers and so on. So that's just one example. But once these computers exist, well, how are you going to be able to write software for 200 qubits? That's a lot. I mean, sort of speaking, wearing the hat of the previous company I worked for, Classic, which that's what they do. They help synthesize algorithms in a way that ends up being more efficient or better than a human could do, especially for a large number of algorithms. And then the next question is, are you just going to take a classical algorithm and try to run it on quantum, or are you going to develop the next Shor's algorithm that's quantum specific to solve different problems?
So coming back to the first part of your answer, where you were talking about different people having different definitions of bigger. So I guess more specifically, there are all of these different metrics and measures coming out, quantum volume, and too many to count. And it seems like many of them are tailor-made by the people who design certain architectures to make their architecture look good on some front. What do you see as the correct way, or a universally acceptable and agreeable way of characterizing how capable a quantum device is in a practical way?
I personally believe in application-specific benchmarks. So if you're trying to solve an optimization problem, then okay, here's the optimization problem. How large and how accurate or how good a result can I get on a given computer? And one of the things that's interesting with our roadmap is that, so okay, I gave you a computer that has 256 or more physical qubits and 10 or more logical qubits. What are you going to use? Are you going to use the logical side with fewer qubits but better, or are you going to use the physical one, just have more and do that? So that's part of the transition, and that's part of the benchmarking that we could do, whether it's simulation or whether it's optimization or something else. And I think the QEDC has done some work on that. Not too long ago, I had an episode in my podcast that was brought several benchmarking experts to talk about different ways to benchmark, whether it's the just qubit fidelity or application level benchmarking. So the short answer is yes, I believe in application-specific benchmarking to determine which computer is best for you.
Well, I agree completely. You can't really go wrong if it's completely pragmatic. A metric can always be fudged in one way or another, but if you can claim to have solved a particular problem, it becomes quite concrete. Thanks for that.
So in the industry, and also to a large extent in academia, the focus on sort of comparing different architectures has been on speed. How fast are you going to solve problems? But there's been less emphasis on the energy cost for running these devices. So, of course, there's a financial interest in wanting to use less energy, but also there's an interest in just being friendly to the planet and ourselves to have large computing devices which don't consume enormous amounts of energy. Can you comment on what is the relative energy cost of QuEra's atomic platform versus some other platforms that might have faster gate speed?
Our platform is very energy efficient, and part of that is because we don't need the cryogenic cooling. So we just need lasers. So our initial computer, 256 qubits, requires about 7 kilowatts of power. 7 kilowatts of power is, let's call it 3 hair dryers. So if you can run 3 hair dryers in your home, you probably have enough energy and I think also enough space to have one of our quantum computers. Next generation computers, well, maybe they end up having 10 kilowatts or 12 kilowatts of power. But this is a far cry from the supercomputers that require megawatts and megawatts. And so I think you're right. There are companies that define success in quantum in being able to do the same thing they do classically, except for a much lower energy cost, while others say, no, I just want to solve a problem that I could not solve classically.
Right. And looking beyond 2026, you mentioned earlier, what do you see or what do you think will be the next big milestone in quantum computing? Is it going to be demonstrating very large scale error correction with fault tolerant processing, or something more directed towards commercially relevant application?
I think they go hand in hand, and I think we spoke a little bit earlier about the goals that the UK national program has set. I think they said 1 million quantum operations by 2028, and then a trillion at some point in the future. So if you're an algorithm designer and I say, hey, here's a system and it's got 100 or a couple hundred qubits and you can do 1 million operations on them, that's powerful. And now, even today, we're starting to see companies that are thinking about how they optimize the resource requirements from quantum computers. The onboard computer at the Apollo 11 lunar mission had, I think, 70 kilobytes of memory altogether, and they were able to program it to get to the moon and back. So if I gave you 2 kilobytes, I can't do it. But at some level, you say, you know what, I can relax this constraint, or I can find some clever trick and I can fit the problem into a computer with 1 million quantum operations. And now it becomes interesting. So a lot of people think about quantum with parallels to AI. And on one hand, what has prevented AI from having that ChatGPT moment 5 or 10 years ago? Some of this was algorithmic development, right? The famous paper, attention is all you need. But a lot of it was just computing power. Once you have enough GPUs and they're fast enough, then you can all of a sudden run these larger networks and execute the same algorithms on a bigger scale. So I think that once we get to computers that can do sufficiently large number of operations, then truly the world is your oyster in terms of the algorithmic opportunities that it offers.
Yeah, I like what you said about the 3 years. It just feels like it's finally getting to a place. So a lot of us have been in the field for such a long time, right? And the joke was quantum computing was always 10 years away. And it's finally getting there. We're finally getting to the 5 years and the 3 years mark. And it's good to see it coming, very, very quickly and actually being able to see the impact very quickly. So another thing is it's a cool field because it is a little bit small right now, which is great that we can have these conversations and have people like you on the podcast. But you also have your own podcast called the Superposition Guy. So how has this experience influenced your work in quantum computing?
Well, I enjoy podcasting, and I think it achieves several goals. I mean, first, I get to meet a lot of interesting people, because after a while, once you've done 20, 30, 40 episodes, I feel like I could reach out to anyone in the industry and said, hey, I have this podcast and this person and this person and this person and this CEO and this leader was on it. Why don't you come and we'll talk? And many times they say yes. So it's an opportunity for me to learn. I've certainly learned I ask only the questions that I care about, that I would be interested in knowing, and hopefully my audience shares some of that taste. It also has been an effective business development tool, because now if the microphone is off, hey, Anastasia, what do you know about QuEra? Would you like to try one of our computers? What is your quantum vision, and can we help fulfill that? So it has helped in that way as well. So I think it sort of serves dual purposes. One, to inform, educate, sometimes entertain the community. People have come up and said, "Oh, I've listened to this episode and I've learned this about that," which is great. But it also serves sort of an egoistic purpose that I just want to learn, meet new people, and sometimes some new business comes out of it as well.
It definitely moves the conversation to a higher level, right? So instead of talking to folks in other industries, maybe, and you have to start with what is quantum computing, you have these episodes where you've talked about it a million times. They can listen to one and really move the conversation in a different field. And yeah, I think another cool thing with having these conversations, right, is these are some of the conversations we also have at conferences, and a lot of people just don't have access to the sorts of folks that you can bring on the podcast that we have on, and just getting the student, the investor, the researcher, the industry expert to get into the field and introduce them to the folks in the space that they can connect with as well.
For a while, I look at the podcast statistics, and for a while, the most popular, most listened to episode was one that I interviewed Peter Chapman, CEO of IonQ, and although he had interesting things to say, I suspect a lot of it was sort of driven by Wall Street and all these analysts that are trading in IonQ stock, and so, oh, what is he saying, and what's new, and what's with this production facility, and so on. That, by the way, got overtaken by an episode with Professor Misha Lukin and two other authors of the quantum error correction article. So that sort of had a broader excitement, at least in my audience, than the commercial version.
Working in the intersection of scientific communication and quantum technology, it has some unique challenges, especially, I guess, in the sense that so much of our normal intuition from everyday computing and what we're all familiar with just doesn't carry across into the field of quantum computing. And so when people talk about developments in quantum computing, it's very, very easy for things to be misunderstood or miscommunicated because of the quite specific nuances. What do you see as the challenges in addressing that and the right way to confront it so that all this miscommunication and misunderstanding that is very widespread, so that that doesn't continue and that gets properly confronted?
I think you mentioned earlier this discussion about quantum volume, algorithmic qubits, these kind of qubits, those kind of qubits. I mean, that probably creates more confusion than it solves it, although it's a nice metric for a particular company to show their progress. This is a science-heavy field. I sometimes joke that I only have a master's in physics, so they barely let me in the door at QuEra without a PhD. But when I was younger, I studied linear algebra, and in linear algebra, very quickly it was, well, let's say you have an eighth dimensional space. So, when you have 1, 2, 3 dimensions, you can say, oh, it's like this, or it's a cube, or and then at some point you say, oh, I'm just going to let the math take me to where I need to go. I can't visualize an 8-dimensional space. I'll just follow the rules. And I think the same is true for quantum. Not everything you can understand, right? The block sphere is really good for a single qubit, but what do you do when you have 17? So at some point, you just trust your education and the math and follow that along.
And can you share a memorable moment at QuEra, or something that sticks out to you?
I think the very memorable moment was the first time we put the computer on bracket. So the company worked super hard, both to actually build the machine, to connect it to the Amazon cloud, to live up to Amazon's requirement on security and uptime and SLAs. And then, we turn it on, and okay, so you open the curtain. Are there going to be people in the audience? And then once we saw these first jobs coming and getting executed and getting results, that was a very gratifying moment for the company, and really the culmination of many months of work. Since then, when the product launched, we only had it live for 10 hours a week. Now we're at 130 hours a week, so more than 10 times that. We've learned how to operate the machine. We've learned how to keep it running essentially all the time. That is also translating into our ability to deliver machines to other countries or other cities. But I think the turning on the bracket service for QuEra was really a defining moment in the company.
Great.
Awesome. So, Yuval, thank you so much for coming on. Where can we find more information about you, your work, your podcast?
So the company is QuEra.com, QuEra.com, like Quantum Era. My podcast is the Superposition Guy on Spotify and Amazon and Google and wherever podcasts are. I'm also pretty active on LinkedIn, both to talk about episodes, but more importantly about other things that are going on in the industry. And really happy to hear from anyone that wants to engage wants to entangle with us on quantum.
Sounds great. Well, thank you so much again for coming on, and thank you all for listening. And like you've all mentioned, if you have any questions, if you are watching this on YouTube, you can comment down below. We'll check that. We can pass on any questions to the guests or for us to talk about in an upcoming episode. And same thing here. You can find the Quantum State on Apple Podcasts, Spotify, wherever you find your podcasts. And see you next time.
Thanks, Yuval.
Thank you very much. Thanks for having me.